Suppose that you're in a manufacturing industry, like you're manufacturing a car or an aeroplane, or any other complicated machine or factory and so on has different components. Okay, so each component may fail, and sometimes some of these failures may be okay for some time. Some of these failures may be fatal. So, for instance, in aeroplanes, if some of small stuff they don't work, may not lead immediately to a disaster, but some other ones they are very dangerous. So, we want to develop some. And then these failures and accidents and hazards and events are random, and we want to develop a theory, solid theory, in order to build, design, and follow up on those things. And this is called reliability engineering. So in 2, 3, 4 videos, we want to learn the basic concepts which will allow you to study, formulate very complex systems very easily. And we see that using a probability background will make everything like a piece of cake. So system reliability is involved in many systems like bridges, car engines, aeroplanes, biological systems, in ecological systems, chain of command in civilian or military organization, may be viewed as assemblies of many interacting elements. And these elements, they have impact on each other and so on. So we want to use. So these elements are arranged in mechanical, electrical, or logical series in parallel or cascade configuration. Sometimes, like in a surgery room, usually they use electricity from the city, but if the electricity from city goes off, automatically backup batteries will power the room. And if the backup batteries they don't work, they use like some gas engine power generator, and if that doesn't work, they do something else. So they have some backups and so on. So we want to define several mathematical tools to evaluate the reliability of such a system. So in easy examples. So this has many applications in industry, such as in quality control of systems, manufacturing, plants, etc. And remember that we don't teach a system reliability course. This could be a couple of graduate courses, but that's exposure will be enough for you to follow up should you get a job. So consider a random variable. So we are considering a very simple subsystem. For instance, for your car, it could be one of the tires. And suppose that X denotes the time that that system or one of the given systems fails. Obviously, if you have 4 tires, then you have 4 random variables. So X denotes the time that your, let's say, right front tire fails to work and cannot continue to operate. So because we assume that at time like 0, the system X is functioning, so X is a non-negative random variable. So at some point you have a failure, okay, in time. So our random variables in reliability theory are usually time of failures. So system reliability is associated with the distribution of these random variable and is defined by the probability that this system does not fail before time t. So we want to know for what period of time, let's say this is t, so this is probability that time t you don't have a failure. For instance, if you have to fly and your flight takes 1 hour, we want that probability that X is bigger than let's say 1 hour to be close to 1, because we don't want a failure to happen before the flight ends. So for that case, for an aeroplane, we want the reliability to be close to 1 up to the end of your trip. After that, if the reliability reduces, we don't care much because somebody will look at it and then resolve the failure. So reliability basically is defined simply as probability that X is bigger than T. So this is called the complementary CDF, cumulative distribution function of X. So the CCDF of a random variable is your reliability. So it's like 1 minus CDF. 1 minus CDF is your reliability, where this guy is the time. Okay, so the time to failure. So your and then if the reliability is very close to 1, that means that your system is reliable. And if reliability is 0, that means that you are very likely to fail. Your system is likely to fail before time t. Another important parameter that usually people define is the mean time to failure. So mean time to failure is that the average time that X takes to fail, this system fail. And obviously this is equal to this integral. Because your distribution is non-negative, okay? So you have, this is your PDF, so it's going to be center of your distribution. And this reliability is always a decreasing function because this is 1 minus CDF and is always equal to, starts at 1. Okay, so this is Rx of t, and t greater than 0, and the mean time to failure is also. Obviously, you can show that the mean time to failure is the area underneath of the reliability, because the reliability function starts at 1 and at infinity it becomes 0. So this area, okay, the area of the reliability is equal to the mean time to failure. Obviously, if the mean is bigger, if the center of distribution is bigger, then this area shall be pushed, so you'll have more area. And obviously, the more area you have here, you are more reliable, because this function is a non-increasing function. The probability that a system functioning at time t fails prior to time x. So the CDF of this random variable x, given the event that we know that the system has functioned up to time t. Suppose that you are at time t, and you know that you are in the airplane, and there you're still flying. So here at time t, but you consider a later time x. Here x is bigger than t. So you want to see what is the probability that you fail before that. So this is equal to probability that x is smaller than x, and given x bigger than t. Okay, so this is obviously equal to probability that x is smaller than x and x is bigger than t divided by probability that x is bigger than t. Okay, so numerator is just the difference between the CDF at this point minus CDF at this point. So you get fx of x minus fx of t, and this is Rx of t. Okay, so so this is the property that a system functions at a system that is functioning at time t fails prior to another time x. So here my objective is to let this x go towards t, so not very long time. So probability that your airplane has fails while it is functioning at time t in near future. So if I take a derivative of that, so d to dx, okay, so denominator is only a function of t, this is a function of t, only this guy is depending on x. If you calculate that, and this guy becomes fx of x divided by Rx of t. And then if I replace these x by t, I get this gets very interesting.